we'll get going. So here we are then. Here's our high pressure that's giving us this nice settled weather. And this happens to be in the north of Scotland, where they've had, as you can see, these isobars quite close together there, so they've had some wet and windy weather in the north of Scotland. Not unusual for the north of Scotland. Here we have different, very quiet conditions. I just wanted to just show you, it so happens that the centre of this high pressure isn't far from southwest Ireland, so let's go back to stuff I was doing earlier in the course and just look at this ascent, this tephigram. And just to show you, this is what an ascent, a tephigram, through the high pressure region looks like. Very light winds at low levels, strong winds obviously at the higher levels, but you see this very, very pronounced inversion layer. There's obviously some boundary layer here, quite a shallow boundary layer, and then this huge inversion and this layer of very, very dry air. This is very typical of anticyclones, strong anticyclones. The whole of this layer here is very dry. The big difference between these two curves mean that the relative humidity is very low there, and that's because the air has descended. And descending air conserves moisture, and therefore when the air descends, it follows the moisture follows these lines here. So as the air comes down, the temperature changes, because radiation can change the temperature, but it can't change the moisture, and so you open up this gap between the two. There. That's not the main issue I wanted to talk about today. First of all, I wanted to just have a look at the forecast. Now, this is the forecast for midday on Friday. So this is where we are today, in this fairly warm, actually, reasonably warm airstream. This is where we're going to be on Friday. So this is midday on Friday, and most of the models agree on this. And here we have this plunge of very cold air coming all the way down from the Arctic. And we're going to be feeling it. It's going to be a lot colder on Friday, so make sure you get your winter woolies out. If we watch this in the upper air, so it'll show you how this cold air. So what's basically going to happen is these blue colours are going to come down over us. So at the moment, these blue colours are up north of Iceland and northern Scandinavia, and we're actually in this warm air. Warm air. It doesn't feel all that warm this morning, but that's simply because of the tendency of because of the long nights at this time of the year. Now, as we come forward, we can start to see, this is Thursday at 6 o'clock, and this is when it all starts to change. And it starts to change as you can see this trough here moving down across the country. And this is now giving us these blue colours. So this trough is extending southwards, and in fact this gradient in temperature just stays to the west of it. We're actually going to have this cold air for quite some time, I think. And these temperatures along here start to become interesting. Now, they're not temperatures, they're thickness, these, but the one to look at is this one. It's the 528 line, because meteorological folklore says that if the 528 line passes to the south of you, then you could have snow. And as you can see, we are in much darker colours than these. We're down here somewhere, and so there's potential for snow actually over the hills anyway. So the forecast actually is for snow over the hills. So you might see some white tops to the Pennines, which is always very pretty at this time of the year. Now, the feature I wanted to, so I'm going to wind this back a little bit. Now, one of the things I've been obviously talking about in these lectures is convergence, divergence, and the link to the jet stream. The bit that I haven't really talked about, I've talked about how a depression deepened yesterday. I didn't really show you why a depression deepened. Okay? So I'm going to try and do that this morning. And I'm going to try and do it by using this feature here. So this is obviously a forecast run, so we're looking at a model. And this is Thursday at midnight, and we can clearly see that there is this big trough in the jet stream over to the east of us, down over here. And then we have this southerly branch here of the jet stream. Now, what we know about the southerly branch of the jet stream is that, well, potentially, this is an area where we could get divergence and therefore upward motion. As we run this sequence forward, and keep your eye on this feature here. So that's already a low pressure system, so it's already got a fairly low pressure actually, for 985 this contour here. But as we keep running this forward, you now see it really starts to deepen. So there's several more contours in here. This is midnight Friday, and as we go through, this thing deepens quite a long way. This is about the 970 contour. So we're seeing the growth of a cyclone, and it is to the west of this jet stream flow. So is that what we would expect from what we've looked at previously? That's what I want to start looking at. So just to look at the time scale, that was that's midnight on Thursday, and we're running the sequence forward to about midday on Friday. Okay, and the thing deepens quite dramatically. Now, first of all, if I go back to Thursday at midnight, so this is a plot of the jet stream speed in colour, and so what we immediately see is that we're in this region here. This low pressure system is around here. It's to the left of the exit of the this jet stream. That's a region where we would expect to see divergence. Now, this is a plot of divergence, so there's a plus sign here, and this is indeed corroborating the fact that there is divergence, upper level divergence here. So that's left exit, and indeed you can see, as you can, well, down here also, right exit, there's divergence, it's a bit of convergence here. As we move the sequence forward, okay, we move the sequence forward, so this is moving it forward 6 hours. Now we can see quite strong divergence. The divergence strengthens, and actually the jet stream also strengthens. And as we move through again, the jet stream is strengthening, so those red colours are starting to appear, and the divergence starts to get large as well. So here we are at midnight on Friday, and we've got a large peak now in divergence here, and a strengthening jet stream. So what's happened during this period is that the divergence is to the left of the jet exit, exactly where we expect it to be, but over this period it's actually strengthened, and it's that strengthening of the divergence at the upper level that's responsible for the decreased pressure at the surface. For the pressure to drop at the surface, you've got to move air out of the column, right? That's the only way you can change pressure, is to have less air above you. And this is what's doing that. It's this divergence. But the question is why? Why is this thing suddenly strengthened? And the clue is in the strength of the jet stream. It is obviously linked. This is the strength of this jet stream is now what causes the jet stream to strengthen? Well, we've heard about the thermal wind equation. The strength of the jet stream is related to the horizontal temperature gradient. So what that suggests is that the horizontal temperature gradient in that region has strengthened, strengthening the jet stream, and in turn strengthening this divergence peak here. You can see that there's even negative values on the other side of this now. So let's have a look at whether that we can find evidence for that. Well, this is again Thursday at midday. As we move through, what we're going to see really is a strengthening. Now, it's a little bit difficult to see this because what I'm going to be pointing out is a strengthening of the gradient, and these are all sort of greenish colours. So unfortunately, the colour scale is not clever. Your eye tends to pick out the yellow because obviously that's how our eyes work. But actually the action is taking place in several shades of green here. So it's unfortunate. As we move through the pattern, we're starting to see a strengthening, and this is what I mean by the strengthening of the gradient. These contour lines here, these coloured lines here, are now the distance between the edge of the blue and the edge of the yellow has considerably reduced. Okay, so we go back and show that again. So here we have the distance between the blue and the yellow, which is there, and as we go forward in time, it gets smaller, like so. The key to this, why has that happened? And this is where the growth of the mechanism for the growth of cyclones comes from. Remember, the growth of the cyclone occurs because the divergence at upper levels increases. That in turn happens because the jet stream strengthens, and that happens because the temperature gradient strengthens. Now comes the feedback. That happens because the cyclonic circulation at low levels around this growing low pressure is piling cold air to the, in this case, is piling cold air to the east. In other words, it's driving this cold front and strengthening the cold front. And so we have this feedback mechanism between the low levels, the lowest levels of the atmosphere and the upper troposphere. And that is the feedback mechanism that is responsible for the growth of cyclones. You basically need, you need this kind of feedback mechanism. It can happen in a number of different ways. In this case, it's strengthening the front. In other cases, it can work by strengthening the trough. I think that's probably what's happening here. But this is an example of a mechanism. So the mechanism in this case then is working through frontogenesis by the cold air being pulled south from the north to the south of this low pressure system. Remember, these are average temperatures in the bottom part of the troposphere, near the surface where these white contours are. It's pulling a lot of very cold air down now and strengthening the temperature, and at the same time the upper air is pulling this warm plume up from central Russia, and so you have this strong gradient there. But that is the essence of why we get growth of cyclones, in particular in the atmosphere, is that you get this strong feedback during the growth phase of the cyclone. And in this case, rather interestingly, it's happening when you've got an alignment, in this case, between the black line and the white line. There, the black centre and the white centre are co-aligned. It doesn't always happen that way. You can see here there's a little bit of a shift. This white one is a bit more to the west from the black one. That's more normal. But it's just to make the point that baroclinic instability, as this is called, the nature of the instability is because of a feedback between the upper and the lower atmosphere. That's just to show you that happening in that case. Yeah? Any comments on that? Okay, so that's the essence of baroclinic instability. Again, to do baroclinic instability formally and mathematically, I would need to take you through a piece of maths called quasi-geostrophic theory, which would take most of my 10 lectures if I did it, and leave you none the wiser probably. Okay, so I'm going to finish off with the lectures then, and these lectures really are intended to look again at this mechanism of convergence and divergence. So following up this idea yesterday when I was introduced the idea of vorticity, I'm now going to apply vorticity dynamics and show how we can look at the same phenomena as we've seen before, but through the eyes of vorticity rather than through ageostrophic motion. Physics remains the same, but the mathematical approach is different. Just to remind you, relative vorticity is defined as, in natural coordinates, u over r minus du dn. N is the unit vector to the left of the flow. Usually I drop the r when I write zeta, and that would mean the relative vorticity. The curvature term and the shear term, sometimes called curvature vorticity and shear vorticity. Absolute vorticity then is the sum of the relative vorticity and F, because that just relates to the fact that the Earth is spinning and imparts the vorticity to the flow just by virtue of where it is. I've put an A there. If I write zeta A, if I write absolute vorticity, I will always put a symbol there, A. So zeta A means absolute vorticity. And again, if I don't use a subscript, it's this one. And then at the end of the last lecture, I introduced this idea of potential vorticity, which is in the formulation I'm going to use here, is basically the ratio of the vorticity to the depth. And the depth can be expressed either as pressure or as Z. It doesn't really matter because the physics is the same. The change in pressure or the change in depth of the air column obviously are equivalent quantities if we're talking about a hydrostatic atmosphere. I'm not going to dwell on this one. That's just to remind you that potential vorticity has other formulations which are more rigorous. And indeed, just remind you that vorticity itself is inherently a three-dimensional quantity. It's the curl of the velocity vector, but we're not bothered by that at the moment. So that's just to remind you. Now I want to take you through a little bit of the science of Rossby waves. So I've used the term Rossby wave, and that's to describe these undulations in the westerlies that we've seen all the time. They're always there, these Rossby waves. And the basic mechanism of a Rossby wave works a bit like this. So why do we get these undulations? Well, if we take a parcel of air here, so this is a parcel of air at A, and if we note that in a few lectures ago we talked about Dyne's compensation. Dyne's compensation tells us that, well, it's just an expression to describe the fact that you get convergence above, divergence below, divergence above, convergence below. You get this vertical dipole in convergence and divergence, right? In other words, the divergence changes sign in the vertical. Therefore, there must be a level in the middle where there is no divergence, right? If you've got negative above and positive below, there must be a level in the middle where it's zero. And this is called the level of non-divergence. It's somewhere in the mid-troposphere. 500, 600 millibars, somewhere around there. Now, the barotropic vorticity equation that I introduced yesterday relates the rate of change of vorticity to the divergence. Well, if there's no divergence, there's no rate of change of vorticity. So the absolute vorticity is conserved at this level of non-divergence. So somewhere in the middle of the troposphere, there's a level at which this is not, at which this doesn't change. And then we can formulate quite a simple schematic argument. We can note that as we go further poleward, F increases. F is proportional to sine of the latitude and therefore increases with latitude. And for example, if we look at this region here, there's the relative vorticity is negative and positive in these regions here because of the curvature of the flow. As the parcel goes northwards from here, let's suppose it starts off from here with a value of no vorticity, say. Let's suppose its vorticity, it's in a straight part of the flow and there's zero relative vorticity here. As it goes northwards, in this part of the flow, it must therefore develop negative vorticity. If it starts off with 0 and F increases, this must go negative. And that negative means that it turns anticyclonically, it turns clockwise. And that's what's happening here. So you get this clockwise rotation of the flow, simply through conservation of vorticity. As you get to the other side, it's now got a velocity that points takes it further towards the south, and the reverse happens. So again, it overshoots, if you like, its original level, and then off it goes, and again curves this time anti-clockwise and in the region of positive vorticity. So the idea of Rossby waves is this exchange of vorticity between the relative vorticity and the planetary vorticity. It's a feature of spinning planets. You see it on other planets as well. One of my colleagues, Paul, who will be teaching this course after I finish today in a fortnight's time, he's built a model of Saturn, for example, and showing Rossby waves in the atmosphere of Saturn. But this is the basic underlying mechanism of Rossby waves. Well, it's not hugely quantitative, that's just really very qualitative. So can we do something a bit more quantitative? Well, yeah, we can. Okay. So we can formally consider this equation, d by dt of the relative vorticity plus f. And in fact, if I just introduce this to you, so if I go to one of these and take down this. So this is this bit of it isn't examinable as such, but because it involves quite a lot of fairly formal maths. It's not particularly difficult, and the reason I'm not over-egging it is because actually even this involves quite a lot of assumptions, because you start off with this idea of a level of non-divergence, and let's face it, we're interested in bits of the atmosphere where there is divergence. But basically what this does is to derive a wave equation. So it goes from here, from this statement about vorticity, and basically goes through and derives a wave equation for these Rossby waves. And that's why we refer to these undulations as waves, in fact. It's because we can go through and do this calculation. I'm not going to completely go through this. I'm just going to point out the features of this. Basically, we start off by looking at a perturbation. So any kind of wave analysis in physics always assumes effectively infinitesimally small perturbations, right? Clearly, we've looked at these Rossby waves. Infinitesimally small they are not. Okay. So again, this is a kind of an abstraction that is not really particularly realistic, but again, it does get us to somewhere. So these perturbations, so these are sort of infinitesimal perturbations, if you like, u is a background wind speed, which just happens to be there. And so that's just that equation written out. Now we use a trick to relate velocity and vorticity. We use a thing called a stream function, and this takes this uses a thing called a Helmholtz decomposition for two-dimensional flow, which basically allows you to take any velocity field in a two-dimensional flow and divide it into a stream function and a velocity potential. This is an irrotational, so the curl of this is obviously 0, and the divergence of this is 0. So this is non-divergence, and that is irrotational. And that's a sort of standard trick in fluid mechanics. So we've already made the assumption that we're looking at a level of non-divergence, so we can kick that term out and we're left with the stream function, and by doing that we end up with an equation, this equation here, which is just in terms of the psi. So this is now an equation. Obviously it's a differential equation, homogeneous, and it's in a single variable. So what do we do with it? Well, whenever you're faced with anything like that, the standard trick is to propose this wave solution to the equation. So this is just really very, very basic sort of theoretical technique there. And so you go through that and you reduce the differential equation to an algebraic equation, and you get this equation, the bottom here. So you essentially get an equation, a dispersion equation. So this relates omega, the wave frequency, to the K, well, K is the, Roman K is the horizontal wave number in the x direction, and then this Greek K uses x and y, and we have this dispersion equation, which is normally written in this form, C is u minus b of the k squared. So it's possible to do this kind of analysis. I deliberately do not expect you to be able to follow every step of that, but if you're interested, then it's on the website and you can have a look at it. What I'm going to pick up at the end is this dispersion equation here. So if you didn't quite follow all of that, then don't get too stressed about it. It's pretty straightforward theoretical techniques, but you may not have seen, particularly the Helmholtz decomposition, which I have no intention of proving. But like I say, there are assumptions that go into here that are not valid in the atmosphere, so we shouldn't overemphasize the importance of this derivation. But picking up this dispersion equation, so it's written in red there, the value of that, if you like, next level of sophistication in analysing these Rossby waves, you actually do something quantitative, and you do end up with something that looks fairly quantitative. And actually, this thing works fairly well. Fairly well, because obviously Rossby waves are rather more complicated than that simple mathematical treatment, but still, an essence of this, the wave speed, the wave phase speed is the wind speed, okay, minus, so it's less than the wind speed, beta, which is the rate of the gradient of f, 2 omega cos lambda over a is the radius of the Earth, and at 60 north you get a value of around 10 to the minus 11, not that the number means a great deal, and then divided by the wave number, so k is the wave number of the wave, in obviously x and y, potentially. And so what this is saying is that if you make k large, this term here becomes small. So k is large, then the wavelength is small, right? So because 2 pi over lambda. So large k short wavelength waves basically travel the same direction as u. So u minus something. So they travel eastward, slower than the wind, so the wind moves through the pattern, which is what we've seen. But if you get very long wavelength waves, this thing can actually go negative. And in fact, long wavelength waves can travel in the other direction. So very large scale Rossby waves travel to the west. And the scale at which that flips over is of the order of 10,000 kilometers. So that's just putting these numbers in there, it doesn't really matter. Putting 30 meters a second in there. Now 10 to the 4 kilometers is not the scale at which we're trying to look at in this course, that we're looking at 10 to the 3 kilometers. So this is a larger scale, a planetary scale, that we're looking at. This absolutely dominates the stratospheric flow. It turns out that, particularly in the winter, the only Rossby waves that actually make it into the bulk of the stratosphere, above about 25 kilometers, are very, very long wavelength waves. Waves that go once around the Earth or twice around the Earth, possibly. And they obviously propagate in this retrograde fashion. Okay, so that's picking up the idea of the waves moving from west to east on the synoptic scale, east to west on the larger scale. But really that's only getting us so far. Again, to do this, to capture the properties of finite amplitude Rossby waves, or these disturbances that are certainly not infinitesimal in their amplitude, we need to use this quasi-dystrophic theory, which I am not going to introduce here because you need to spend a lot of time to pick that one up. So we won't go further with that mathematical idea. What we're now going to do, though, is to turn back to the main theme of all of this, which is to look at convergence and divergence, because after all, that's what we're after, and the link of that, of course, to the growth of cyclones and anticyclones. Now, we talked about the level of non-divergence earlier, and the level of non-divergence is in the middle of the troposphere. But we still, as we can see, as we're very familiar, these Rossby waves are coherent in altitude. So you get the same pattern at 500 millibars as you do at 300 millibars. But the wind is stronger in the upper troposphere. That's called the jet stream, right? So as you go up in the atmosphere, the wind gets stronger. Now what does that mean? Well, if this amplitude of the wave is the same, it doesn't change much with the altitude, then this latitude excursion of the wave, delta y, doesn't change. So the difference in F as you go between the trough and the ridge doesn't change. But because the wind gets stronger, these terms get larger, particularly U over R. R stays the same, U gets larger, and so now we find the excursions in F, in zeta, the excursions in vorticity are larger than the excursions in F. So what does that mean? Well, it means that absolute vorticity now, the sum of vorticity plus F, is a minimum in the ridge and a maximum in the trough, because the variation in vorticity overwhelms the variation in latitude, in F due to latitude. Absolute vorticity is always positive. Well, I say it's always positive. It's a bit of a cheat since I'm writing a grants application to investigate what happens when it goes negative, but nearly all of the time absolute vorticity is positive, because if absolute vorticity goes negative, the theory, dynamical theory, tells us that it's a little bit like absolute stability going negative in the vertical. When that happens, you get convection, dry convection. And when you have negative absolute vorticity, you get something similar, but in the horizontal, thing called inertial instability, which essentially would mix out the instability, the region of negative vorticity. What we don't know is what timescale that happens on and why it happens. So we know why such a region can be produced, but we don't know how long it will last. So anyway, that's not the point of this. This is just saying that absolute vorticity pretty much all the time is positive in the northern hemisphere. And therefore we can use it for this idea of conservation of potential vorticity. Because if this thing's always positive, then we're back to this picture where short and thick morphs to long and thin, and we get, so if the vorticity increases, the depth of the column increases, and because, as we're looking on this diagram, the top of this is at the tropopause, vertical motion decreases with altitude in the stratosphere. The static stability of the stratosphere inhibits vertical motion, and so basically the tropopause doesn't move very far, so it's the bottom of this parcel that has to do the biggest displacement, and therefore we get downward motion in this region of the atmosphere. So increase in vorticity, downward motion. So increase in absolute vorticity means an increase in delta P, and therefore downward motion. And so this is another diagnostic of downward motion. So this is our PV again. So let's apply this then to the two cases that we, maybe if I, that's easy for you to see probably. Okay, so this is back to this canonical jet streak. Now, when I used this before, I was looking at ageostrophic motion. Now I'm going to be looking at vorticity. So this is a chart. So these are lines of constant potential height on a pressure surface. And then you've got this pinching of these contours in the middle, which coincides with a jet maximum, the usual way. And we know, of course, that there's this convergence-divergence pattern around the jet stream because we saw that before. But let's not analyze this now from the perspective of vorticity. So let's look first of all to the north of the jet. And what's happening here? Well, these lines, these contour lines, are getting closer together. So as we come down this line here, the distance to this middle contour decreases. So what does that mean? Well, basically, it makes the wind speed stronger, because that's what's happening here. So we've got a maximum in the jet. Out here, the flow isn't affected. So we've got the same flow here and here, no difference. So what's happening? Well, the UdN is negative because n is to the left of the flow, and u is a maximum here and undisturbed here. So dUdN is negative and large in this region here. dUdN is negative in this region because there is a sort of maximum in the wind, but it becomes more negative. So minus dUdN, which is the vorticity, becomes positive. So we have maximum in vorticity in this part of the flow. Maximum in vorticity because it's a maximum gradient in wind, because the jets is here and this flow it hasn't changed. And what does that do? Well, if the parcels of air that start here, so the increase in vorticity must force an increase in depth, and that's consistent with this idea of convergence in that part of the flow. And the rest of the pattern follows by symmetry. Here we have jet here, undisturbed. So again, this time du by dN, u increases as you go to the left. So du by dN is increasing, so minus du by dN, which is the vorticity, becomes negative. So you go, the absolute vorticity reduces as you go through from here to here. And so that means less vorticity, and it goes from long and thin to short and fat. And therefore you've got divergence in this region here, the other side. So forces, so this gives you the same pattern, so we get the same answer, but it's just looking at it from a slightly different perspective. Throughout this pattern, F is the same. F doesn't change because the whole thing is going from east to west. So I haven't involved F in that calculation at all. That's just to do with changes in the vorticity. So vorticity, the absolute value of the vorticity, the relative vorticity, maximizes around the jet, positive in this region, negative in this region, and so the absolute vorticity reaches a maximum and minimum. If we then take the other example, which is a Rossby wave, same idea as before. So this is pretty familiar. You go from A to B to C, and again, minimum in relative vorticity, maximum. And so what happens? Well, absolute vorticity increases going from here to here. Increase in absolute vorticity means that the column has to stretch. Stretching of the column is convergence, and that gives you downward motion here, and the opposite here, upward motion here. In the troposphere, downward motion generating anticyclonic behavior at the surface, and upward motion tending to encourage the growth of cyclones on this side. So you see cyclones like we did earlier this morning in this branch of a Rossby wave. You don't see a cyclone developing in this branch of the Rossby wave. So upward motion, oh, I got this wrong, so the colours are the wrong way around here. The words are correct. Upward motion promotes deep convection in cyclones, and downward motion promotes clear skies and anticyclones. Sorry about the colour thing there not being quite right. Okay. I'm going to do a couple of examples with you, just because if you look at the other side of your one of them is on the handout, this one isn't, but obviously you have access to this. Now this is really just to go through the kind of words. So if you're trying to do this with the example sheet that I gave out last week, then you'll see questions like this, and questions like this will come up in the exam again. So this is just to try and disentangle what the words mean. When you're faced with a problem like this, draw a diagram. First thing you do is draw a diagram. Don't try and analyze it without a picture. Otherwise you won't be sure what it's saying. And what it's saying is that the tropospheric air, so jet stream, flows at the speed of 30 meters a second, so that's a constant speed in this artificial example, through a sinusoidal trough ridge pattern. So now it's telling you that we're looking at something that looks like, oops, where are we? That. So looking at that example. And it's giving us the peak to peak amplitude of 500 kilometers and wavelength 3,000 kilometers. Calculate the change in absolute vorticity between ridge and trough and derive the fractional change in the depth of an air column as it traverses the pattern. So obviously that's the kind of thing that I was just talking about, and I'll now do it. You need a little formula here. The radius of curvature of this function is ak squared to the minus 1 at the crests. Okay, so that's just so that you can calculate the radius of curvature. Clearly, to get the vorticity, you need u over r, and to get r, you need to know that little formula. So that's where that's coming from. So there's the picture. Always draw a picture. What have we got? This is 3,000 kilometers. That's a wavelength. That's a is 2 pi over lambda. This is 500 kilometers peak to peak, so 250 kilometers is the amplitude of the wave, standard in the A sine thing. 30 meters a second is the speed. So calculate the radius of curvature. The amplitude is 250 kilometers. The wavelength is, we've given that, 3 times 10 to the 6, 3,000 kilometers. Be sure to always convert these to the correct units. So K, the wave number is there, and therefore A times K squared, that's converted to meters, and so it gives us a radius of 916 kilometers. So that's 1 over this thing here. So U over R is just 30 over 916, 30 meters a second over 916,000. And we get 3.28 times 10 to the minus 5. So that's positive here and negative here. The way this is being drawn, it's symmetrical. So that's a fairly straightforward application of the formula that was given in the question. To work out the vorticity, we now have to add F. Now, the problem says 50 north. So this line here is 50 north. What I'm going to do in this question is to allow for the change in latitude going to here and going to A and B. 111 kilometers is, so there's the formulae, but 111 kilometers is 1 degree of latitude, and so 250 kilometers corresponds to 2.25 degrees of latitude. That's just using this easily memorable formula like that. And so the trough is at 47.75 degrees, the ridge at 52.25 degrees, and we can calculate F in the two, 1.08 and 1.15. We can see that in this case there isn't much difference in F. And so when we add the vorticity to F from the previous slide, we get 1.41 times 10 to the minus 4 and 0.82 times 10 to the minus 4. It's a fairly simple thing to do. And as we can obviously see, it's larger in the trough than it is in the ridge, which is thankfully, even though the vorticity, the F is larger in the ridge, as we said before, variations in relative vorticity overwhelm those in F at this scale. So you get that. And then it's a straightforward thing to work out the fractional change in the depth of an air column. In this example, I've just taken the straight part of the flow, so that's F at 50 north. No vorticity there, so the relative vorticity, so the absolute vorticity is equal to F. And so the trough divided by the straight, this is just applying conservation of PV, and we get that. So that ratio gives you 1.26, and similarly here, ridge divided by the straight part, that gives you 0.73. You divide those two, and get a number that's around 1.5, 1.4, 1.5. Quite a lot, quite a substantial stretching actually. So it's not an infinitesimal amount of stretching, and in shorter ways you can end up with very, very very, very strong stretching. So that's the kind of thing that you would need to do to answer the questions on the example sheet. That's that one. Another example, another similar sort of thing. This is the one that you do have a copy of. A zonal jet stream, what does that mean? That means it's going from east to west. So when you see, from west to east. So when you see the word zonal, it means it goes along a latitude line. Okay, so straight away you know, okay, this is the one that goes straight across the page. It develops in a uniform zonal flow of 30 meters a second, that's 60 north. The jet has a maximum speed of 80 meters a second, so we're going to look at this example. Oops, where are we going in too fast? This one here, so it's that case, right? So we're looking at that. Jet has a maximum speed of 80. The cyclonic side is 200 kilometers wide, and the anticyclonic side 600 kilometers wide. And that's also very typical. These things are not symmetrical. They're usually much tighter on the cyclonic side. If the initial depth of the column of air which enters the jet is 100 millibars, use the barotropic vorticity equation to estimate its depth at maximum velocity if it's positioned forward, equatorward, directly upstream of the jet core. What limits the accuracy of these estimates? So that's the kind of question that's being asked here. You don't need to write that down because it's all written down for you. Here's a diagram. Okay, so here we have our jet streak here is 80 meters a second. Everywhere else in the pattern is 30 meters a second. That's what the question says. And this is the cyclonic side, that's the anticyclonic side. This one much tighter than this. Why? Well, it's because of this limit of absolute vorticity having to be positive. If it goes negative, then the atmosphere basically rearranges to stop that, and that basically means that there's a limit to the vorticity that can develop in this region. Shear vorticity is what we're interested in here. There's no rotation, so it's minus du dn, and so in the top part here we have 80 minus 30 du, and then this distance which is 200 kilometers, and so the difference 80 minus 30, 50 over 200 times 10 to the 3, 2.5 times 10 to the minus 4. So it's around 2 times f there. F is 1.26, so the absolute vorticity 3.76. So we can see we can get very large values of vorticity in these shear zones on the edge of a jet stream. So shear vorticity can be very large. So that's 3.7, that's 3 times F. And again, if you apply the conservation of PV, what does it? It starts off with a vorticity of F, okay? And so delta P at 1 is, so 1 is here, so if we start off with 100 millibars, then it's roughly a factor of 3, well, it's very close to a factor of 3 larger. So the expansion of the column of air is a factor of 3 in this diagram. On the other side, similar sort of calculation, but this time 600, and so obviously the shear vorticity is 0.833, but this time it's negative, so we have to take that away from this, and we get 0.427, and this time we get another factor of 3, but in the other direction. So it expands by a factor of 3 on this side, and it shrinks by a factor of 3 on this side. So you get very, very strong vertical motions in this hypothetical case here. So in other words, very strong divergence here, and very strong convergence here. If you look at a parcel of air going along the axis of the jet, what happens? Well, nothing happens, because this is a maximum, so there's no gradient here, because it's at the maximum, and so the vorticity stays as it is, and a parcel of air going down the middle like that would not be affected by the stretching. Actually, parcel of air doesn't follow straight through here. It has to do a bit of a diversion to the left simply for conservation of mechanical energy, but there's no change in its depth. And I could possibly leave you with that picture. That's just putting everything together and showing you that as you add the two different types of pattern, The regions that we're most interested in are, so this is where you're downstream of a trough and also at the jet exit, and you get these two particular regions downstream of the trough and jet entrance regions. And so both of those are very favourable regions for growth of cyclones. Okay, so I shall stop at this point, and that will be me done with you for now. You have a week of apparently reading, or happy reading, next week, and Paul Connolly will be here in 2 weeks' time to take on the course. Okay? Any questions or comments? Right, everybody happy? No questions, no comments. Who's got the clicker today? You have, right. So you can bring it back now. Thanks very much. Okay. Oh, yeah.
Quick question about the first example sheet.
Yeah.
I was looking at it and I saw there was a lot of drawing tetragramms.
Yeah.
And I was wondering if there was somewhere to find like the backing of a tetragram, because my art skills are not brilliant. If I
If you go on the web,
I
I took it down. But if you go on that web page, you'll
so I was
find.
looking on the web page and I couldn't find one. I might have just been blind,
You
but
were, sorry.
no, it's fine. Because I was still looking at the sheet and I was like, I cannot draw all those lines.
No, you can't. And you shouldn't even try. Yeah. Okay. So these, yeah. Have you looked at
Oh, right. Okay.
them? That's a ping of a tetragram.
Right.
Or if you prefer script as a postscript.
Oh, thank you. Okay. So I was looking at.
I don't think this is a
it.
postscript viewer on it, but if you've got
Yeah,
postscript
that's
viewers,
fine.
that's fine. Or if you really like detailed ones, you can get coloured ones. Well, there you go, coloured one.
Oh wow, that
That'll
looks
blow your
scary.
mind. That will. Yeah, but you can easily get them off
Okay.
there.
Oh, great. Thank you. Also, I just wanted to thank you because I found this course like so interesting. So.
Oh, good. Thank you very much.
Yeah,
for
I
that.
really
That's
enjoyed
good.
it.
Oh,
Thank you.
Yeah. Hope you enjoy the rest of it. Thanks very much.